Hello, everybody. Welcome to another episode of I missed class, so now I got to catch up on lecture. Today we are going to talk about how to find patterns in polarity of molecules. So we've been taking a look at polarity in bonds, what happens when two atoms are playing tug of war with each other. But what happens if you are trying to look at polarity across an entire molecule? So this time you have to take into account the polarity of all the bonds and see if there's electronegativity differences across that whole molecule. So to review, we're going to take a look at a couple of examples, starting with water, our favorite molecule. So if you take a look at the bonds here, I've given you, or the pictures here, I've given you the Lewis structure on the right. And then on the left, I've given you a screenshot from the gizmo that we were using. So I wanted this to look like something that was kind of familiar to you, because if you look at this, it's got a really nice color coding situation to it, right? If we think back, what did that red space mean? It meant that that part of our molecule was negatively charged. The blue space meant that there was a partial positive charge on there. And if it was purple, it meant things were neutral. So if we're trying to figure out first if the bonds in this molecule are polar or nonpolar, what do we have to consult? Electronegativity tables. We are trying to compare the electronegativity of each of these elements, and then we subtract them to take that difference. If the difference is within a certain range, it's going to tell you if the bond is nonpolar versus polar. So if we took a look at the electronegativity differences between oxygen and hydrogen, what we would find is that this bond is really significantly polar. So the bonds in here are polar bonds. Remember that value is about 0.4. So if it's 0.4 above, we're looking at a polar covalent bond. If it's 0.4 lower, we're looking at a non-polar covalent bond. So in our structure, we can represent the polarity of bonds by using dipole arrows, which you should have learned about from a previous notes section. So a dipole arrow is used to show the direction in which electrons are being pulled, which is inducing that partial positive and partial negative sides to your bonds and your molecules. So the directions will flow towards the more electronegative atom. That makes sense, right? If something is more electronegative, it's going to pull electrons in that direction because it's really, it either is something that is really close to being stable, having that filled octet, so it really wants to gain those electrons to pull towards it. Things that are smaller atoms are more electronegative because they experience really strong forces of attraction with their outer valence shell. But in this case, between oxygen and hydrogen, oxygen is clearly the more electronegative atom, so electrons are going to be pulled towards oxygen. And we can represent that with our little dipole arrow here. We put a little positive end on the end of that bond to show that the partial positive is going to end up being on the hydrogen end. So I'm going to do those for both of those bonds here. On the Lewis structure, you can draw them just like that. If you had something that were in which the bonds were not polar, you would just not draw the dipole arrows, right? Because we're just showing that electrons are being shared equally in that bond. So now what we have to decide is the molecule as a whole polar or nonpolar? So really, what we have to look at is its geometry. The geometry helps us determine polarity of a molecule. If we look at this water here, it's got two atoms attached to the central atom with two lone pairs. These lone pairs are hanging out in orbitals on top of the oxygen. And this is going to have a bent geometry. So think about what that looked like in three-dimensional space when we were building our molecules. The top half of this molecule is significantly more negative than the bottom. Why? Because of those lone pairs. Those lone pairs are hanging out over the top of oxygen, floating around in those orbitals, just doing their thing, and they're just straight up negatively charged, right? So on top of the bonds being polar and oxygen taking in electron density from hydrogen, it's also got lone pairs on top of it, making the top part of this molecule have that partial negative charge. That's where all of our electron density is hanging out in this molecule. That means that the bottom half of our molecule is going to be left with a partial positive charge because electrons have moved towards the top. So we use these delta symbols that we learned about to represent the molecular polarity. So remember that this is a molecule still, right? So we are still sharing our electrons. This is not something ionic. This is why we use these lowercase deltas. There has not been a full transfer of electrons here. One thing hasn't fully lost, one thing hasn't fully gained. That's what an ionic bond is, right? So in that case, we would draw our positives and our negatives showing that transfer of electrons. But here, our molecule can be polar, and they can still have charges in it, but we call them partial charges. The top part of the molecule is a little negative charged. The bottom is a little positive charged because those electrons are still being shared within those bonds. So check, we used our deltas, yay! All right, so this is a case where we had polar bonds and a polar molecule. Let's take a look at our next example. This time here we got carbon tetrachloride. So you got carbon hanging out in the middle, you got chlorines on the end. We have to first decide, are the bonds in this molecule polar or nonpolar? So we grab our electronegativity table, we find carbon, we find chlorine, we take the difference between the two, and we end up seeing that the difference in electronegativities is less than 0.4. If the electronegativity difference is less than 0.4, that indicates that these bonds are in fact polar. Oh, I forgot to write this up here. The molecule is also polar. All right. So to label the areas in which the electrons are moving, we have to consult our electronegativity table to find the more electronegative atom. Spoiler alert, is chlorine. That one should be fairly obvious to you, right? Chlorine's got 7 valence electrons. It only needs to gain 1 more. And while it's a larger atom than carbon, because it has that extra shell with filled electrons in it, it's definitely more electronegative, way closer to being stable. So that's going to take our electron density and it's going to pull electrons towards chlorine. And if we look at our gizmo picture, that is backing us up, right? We see that negative end to each of those chlorines showing that there's way more electron density there, leaving the carbon with that partial positive charge. So here we definitely have polar bonds. We labeled our areas, yay. Now, is this molecule as a whole polar or non-polar? Before we answer that, think one real quick, what's the geometry of this molecule? 4 bonds, 0 lone pairs, tetrahedral. So this thing's clearly tetrahedral. What we have to decide now is the whole molecule going to be polar or non-polar? So think about it for a second. This chlorine is pulling electron density that way, and this chlorine is pulling electron density this way. So remember, our atoms are just playing tug-of-war with those electrons. If you have 2 of the same atoms, equivalent electronegativities, and they are pulling with the same amount of force in equal and opposite directions because they have equivalent electronegativities, what's going to happen is that these things cancel each other out. And it happens on this side too. This pulls to the right, this pulls to the left. Just in our Lewis structure again, we have to think about it in 3D shapes too. So those 2 things are going to cancel out. So what's happening with all of those forces that are pulling those electrons in different directions is that they're completely canceling each other out, which is causing this to become a nonpolar molecule overall. There is no difference in electronegativity across the whole molecule. So even though our bonds in this case are polar, the molecule as a whole will be wait, hold on, what did I just say? Even though the bonds in this molecule are polar, the molecule overall will be nonpolar because these bond polarities cancel each other out. Okay, so this is bent, this is tetrahedral, but what we really want to do is not really take this by a case-by-case basis. We want to be able to look for some patterns. When can I get a geometry and know that for sure it's always going to be polar, maybe it's always going to be nonpolar? Let's see if we can figure it out. So let's take a look at the next page. In this top box here, you've got 4 molecules to look at. What I want you to do is just pause the video really quick and see if you can figure out what do these molecules have in common. Then you can write them in this space right here. After you've taken about a minute and a half to write some things down, come on back and let's talk about it. Okay, I'm definitely going to assume that all of you were so great students, such great students, and you definitely paused the video and did this for me. Thank you. Okay, so what do these molecules have in common? There's a couple things that you could have picked out. One of the most important things that you should have picked out, though, is that if you take a look at that central atom in the middle, every single one of those atoms has at least 1 lone pair on it. And that's critical here. What else you should notice is that from the pictures with the gizmos, you see deltas all around these molecules. What does this tell us? It tells us that all of these molecules are polar. So all of these molecules are polar. All of them have a lone pair on the central atom, and this actually leads us to develop a rule. If your central atom has at least 1 lone pair, the molecule will always be polar. Why? Because you got free lone pairs, dude. Those free lone pairs are just straight up negative charge floating around on that part of the molecule, pulling electron density in that direction, inducing that negative charge, which then will induce a positive charge on the other side of the molecule. So let's take a look at these geometries we got here. NH3, 3 bonds attached, 1 lone pair on the central atom. That's gonna be trigonopyramidal. Woo! All right, NCl3, 3 atoms attached to the central, 1 lone pair. Same. Ooh, trigonopyramidal. Interesting. All right. Water. Water we did on the previous page. 2 bonds, 2 lone pairs. Bent. OCl2. 2 bonds, 2 lone pairs. Not linear. This is bent. Don't fall into the trap. Remember that Lewis structures are 2-dimensional. They show you nothing about 3D geometry. So even though this thing looks linear on paper, it's not. 2 bonds, 2 lone pairs is going to look like this thing right here. Those lone pairs, those negative charges are pushing down on those chlorines, repelling those electrons in the chlorine valence shells, causing this bent shape. So can you think of any other geometries that we have learned out of our 5 that also have lone pairs on the central atom? Answer should be no. Think about linear, no lone pairs on the central atom. Trigonoplanar, no lone pairs on the central atom. Tetrahedral, no lone pairs on the central atom. So really what this is saying is that if you have a trigonopyramidal or bent, these are your always polar geometries because of those lone pairs. And you might be saying, hold on a second, Ms. Lambert. Things look a little fishy here. Take a look at that NCl. I see a lot of purple there. And you're right. Take the electronegativity differences between N and Cl. You're going to have a nonpolar bond. So the bonds holding this molecule together are not polar, but the molecule is. The molecule is because of the lone pair on top of nitrogen. Because of its geometry, this thing is polar as a molecule. So remember, bond polarity and molecular polarity don't necessarily have to do with each other. You can have something that's non-polar bonds, but a polar molecule, and vice versa. So you have to check both. Or you have to develop your patterns in polarity, which we're doing right now. All right, let's take a look at these bottom ones. Okay, take a second, pause the video. This one should take you 30 seconds tops. What do these molecules have in common? Hi. Okay, welcome back. I'm assuming, again, you all were such good students and you paused the video. So what do these molecules have in common? First of all, they only have 2 atoms, which means that their geometry is clearly linear. That's what they've got in common. We got all linear geometries here. But what's the biggest difference that you notice about these? This one right here is 2 different atoms. This one right here is the same atom. This one right here is the same atom. Okay, so what does that have to do with what we're talking about? Well, let's talk about polarity. CO clearly is polar. It's got electronegativity differences. H2 and N2 are not. So this thing here is polar. These ones here are nonpolar. Why are H2 and N2 nonpolar? If you were to find the electronegativity difference between those atoms to figure out if the bond between them is polar or not, what would it be? It would be 0. They have the same electronegativity. So the same thing minus the same thing gives you 0. So these 2 molecules here are incredibly nonpolar. They are sharing their electrons equally between them because they are the same atom. So their electronegativity difference is 0. What about carbon monoxide, CO? Well, those 2 things clearly have a difference in electronegativity values because they are not the same atom. So this brings us to this idea of symmetry. If you have a molecule that is symmetric, what would that mean to you? It would mean that it's the same on every side, right? Same across the whole molecule. If a molecule is symmetric, it's going to be like H2 and N2, the same across the whole molecule, therefore it's going to be nonpolar. There are no differences in electronegativities that are pulling electrons in one direction, which is causing the molecule to be nonpolar overall. What if a molecule looks like CO? You have something that's asymmetric now, not the same across the whole molecule. Well, clearly, if it's not the same across the whole molecule, then we're going to have electrons that are being pulled in one direction, which is going to cause this to be a polar molecule. So these are linear molecules, but they're only made of 2 atoms. Let me give you another example. Let's say I gave you something like carbon dioxide this time. Let's analyze this cutie real quick. So first things first, we already see that the CO bond is polar, and oxygen is clearly the more electronegative atom. So in our bonds, we can draw those little dipole arrows to show that electron density is being pulled towards oxygen. So our bonds here are polar. What about this molecule overall? Well, those 2 arrows are pointing in equal and opposite directions, which means they're canceling each other out. This molecule is symmetric, so this molecule will be nonpolar. So if something is linear, you have to take a look at the terminal atoms to help you figure out if the molecule will be symmetric or asymmetric, therefore polar or nonpolar. This atom in the middle is what we call the central atom, and as a reminder, these atoms on the end are what we call the terminal atoms. So let me give you another linear example. All right, what about something like this? Okay, HC, take that electronegativity difference, that is a nonpolar bond. Cn, that is a polar bond. It's polar in this direction, pulling electron density towards nitrogen. Ooh, and she's also got a lone pair. That means this thing is super pulling electron density towards nitrogen, which is going to induce a partial negative charge on this side of the molecule, leaving this side to be partially positively charged. This is a polar molecule. It's also asymmetric. It's not the same across the whole molecule. So again, asymmetric, polar molecule. All right, let's go back up and let's talk about tetrahedral. So tetrahedral, this molecule here we said was nonpolar. Do you think that there might be a case where tetrahedral could be polar? What if I gave you this? We know that this thing here is a polar bond. Okay. Are all our terminal atoms the same? No, they are not. Since our terminal atoms are not the same, electrons are in fact going to be pulled in one direction, going to make this part of the molecule partial negative charge. This side of the molecule, partial positive charge. So this means our molecule overall will be polar. And this one's got a mix of polar and nonpolar bonds. So with linear, we have to use the symmetry to justify the polarity. With tetrahedral, we also have to use the symmetry to justify the polarity. We have to decide symmetric or asymmetric. The last one that we haven't talked about, our last geometry, is trigonal planar. So let me give you two examples. This is called formaldehyde. And then I can give you, how about this one? So the other reason why I want to bring up this boron trifluoride molecule, you might be like, Miss Lambert, boron's only got 6 electrons on it. What the heck is going on? So it turns out boron's weird. Boron can be stable with just its little 6 electrons on it. So if I give you something like this and you count up your valence electrons and you draw your structure and you're like, what the heck? I am out of electrons. What's going on? Do I need to share this one here to make boron stable? The answer is no. No, for 2 reasons. Boron can be stable with just its 6 electrons, but fluorine and chlorine and bromine and iodine, those halogens there, think about how many electrons they can accept to fill before they're stable. Only 1. So we said they can only form single bonds. So here, fluorine cannot even form that double bond, which is another justification for this Lewis structure here. So boron is stable with just its 6 electrons. Know that, learn that, love that. All right, so back to trigonal planar. Remember, the whole point of trigonal planar was that these angles were all the same. Everything was equidistant from each other. So let's take a look at boron trifluoride. Are these things polar bonds? Yeah, they super duper are. And electron density is being pulled out towards fluorine, our most electronegative atom on the table. So this thing is perfectly flat. The angles between those fluorines are exactly the same, which means it is a perfectly symmetric molecule. And these polar bonds will cancel each other out since they're pulling electrons in equal and opposite direction, meaning this is a non-polar molecule overall. So again, with trigonal planar, we also have to look at symmetry to justify polarity. All right, CH2O. Take a second. Are these bonds polar or not? The CH bond is not polar. The CO bond is polar. Oxygen's pulling electron density that way. Oof. And it's got 2 lone pairs on it. Dang. This thing is definitely going to induce that partial negative charge, leaving these to be partial positive. So this is asymmetric, and therefore this is a polar molecule. So just to recap, bent and trigonal pyramidal, always polar because of the lone pairs. Things that are linear, things that are tetrahedral, and things that are trigonal planar, you have to determine the polarity first by looking at the symmetry of the molecule. All right, what I would recommend you do now is 1, take a quick little brain break, but then 2, go do some practice problems that I've linked into Canvas for you. Bye.